Welcome to this series of supply chain lectures. I'm Johannes Vermorel, and today I will be presenting number 1 at the SKU level in the M5 forecasting competition. An accurate demand forecast is considered as one of the pillars of supply chain optimization. Indeed, every single supply chain decision reflects a certain anticipation of the future. If we can gather superior insights about the future, then we can derive decisions that are quantitatively superior for our supply chain purposes. And thus, identifying models that delivers state-of-the-art predictive accuracy is of primary importance and interest for supply chain optimization purposes. Today, I will be presenting a simple sales forecasting model that, despite its simplicity, ranked number 1 at the SKU level in a worldwide forecasting competition known as the M5, based on a dataset that was provided by Walmart. There will be 2 goals for this lecture. The first goal will be to understand what it takes to achieve state-of-the-art forecasting, sales forecasting accuracy. This understanding will be of foundational interest for later efforts at predictive modeling. The second goal will be to set the right perspective when it comes to predictive modeling for supply chain purposes. This perspective will also be used to guide our later progression in this area of predictive modeling for supply chain. The M5 was a forecasting competition that took place in 2020. This competition is named after Spyros Makridakis, a notable researcher in the field of forecasting. This was the 5th edition of this competition. Those competitions happen every couple of years, and they tend to vary in terms of focus depending on the type of data set that was used. The M5 was a supply chain related challenge, as the data set that was used was retail store data provided by Walmart. The M6 challenge, which is yet to happen, will be focusing on financial forecasting. The data set that was used for the M5 was and remained a public data set. It was Walmart retail store data aggregated at the daily level. This data set included about 30,000 SKUs, which retail-wise is a fairly small data set. Indeed, as a rule of thumb, a single supermarket typically hold about 20,000 SKUs, and Walmart operates over 10,000 stores. Thus, overall, this dataset, the M5 dataset, was about less than 0.1% of the whole Walmart scale dataset that would be relevant from a supply chain perspective. Moreover, as we will see in the following, there were entire classes of data that were missing from the M5 dataset. And thus, as a result, my approximate estimation is that this dataset is actually closer to 0.01% of the scale of what it would take, at the scale of Walmart. Nevertheless, this dataset is plenty enough to do a very solid benchmark of forecasting models. In a real-world setup, we would have to pay close attention to scalability concerns. However, from the perspective of a forecasting competition, it is fair to make the dataset small enough so that most methods, even the widely inefficient method, can be used in the forecasting competition. Also, it ensures that contenders are not limited by the amount of computing resources that they can actually throw at this forecasting competition. The M5 competition included 2 distinct challenges known as accuracy and uncertainty. The rules were simple. There was a public data set that every participant could access. And in order to participate to one of those two challenges, or the both of them, each participant had to essentially produce a data set of its own, which was its forecast data set, and submit that to the Kaggle platform. The accuracy challenge was about delivering an average time series forecast, which is the most classic sort of form of forecast. In this specific situation, it was about delivering daily average forecast for about 40,000 time series. The uncertainty challenge was about delivering quantile forecast. A quantile are forecast with a bias. However, the bias is intentional. This is the whole point of having quantiles. This lecture focuses exclusively on the uncertainty challenge. And the reason is that in supply chain, it's the unexpectedly high demand that creates the stockouts. It's the unexpectedly low demand that creates the inventory write-off. Costs in supply chains are concentrated at the extremes. This is not the average that interested us. Indeed, if we look at what does the average even mean in the situation of Walmart, it turned out that for most products in most stores for most days, the average, the sales that is going to be observed is zero. And thus, most product, while it is actually straightforward to produce an average forecast that happens to be a fractional sales, so it is relatively straightforward to say my forecast for this product and this day is 0.1 unit. Such average forecasts are very, I would say, underwhelming as far supply chain is concerned. Indeed, if you have what does it mean to have a forecast at 0.1 unit if your options are either you replenish 0 or you replenish 1 unit? In general, I would say from a supply chain perspective, average forecasts are quite of little relevance, and retail is not in a unique position here. It is pretty much the same sort of situation whether we are discussing about FMCG, aviation, manufacturing, luxury, practically every single other vertical. Back to the M5 uncertainty challenge, there were 4 quantiles to be produced, respectively at 50%, 67%, 95%, and 99%. You can think of those quantile targets as service level targets. I'm simplifying, but that would be the loose equivalent if I was speaking in, I would say, strict supply chain terms. The accuracy of those quantile forecasts were scored against a metric known as a pinball loss function. I will be getting back to this error metric later on in this lecture. There were 909 teams competing worldwide in this uncertainty challenge. A team from Lokad did rank number 5 overall, but number 1 at the SKU level. Indeed, while SKUs represented about 3/4 of the time series, in this challenge, there were various aggregation levels ranging from the state, as in the United States, Texas, California, etc., to the SKU, and all the aggregation levels were equi-weighted in the final score of this competition. Thus, even if SKUs were about 3/4 of the time series, they were only about 8% of the total weight in the final score of the competition. The method used by this team from Lokad was published in a paper titled A White Box ISSM Approach to Estimate Uncertainty Distribution of Walmart Sales. I will be putting a link toward this paper in the description of this video after this lecture is complete. You will find all the elements in greater details. For the sake of clarity and concision, I will be referring to the model presented in this paper as the REMT model, simply named after the initials of the 4 co-authors. On the screen, I've listed the top 5 results for DiEM5 obtained from a paper from Makridakis that provide general insights on the outcome of this forecasting competition. The fine print of the rank is quite dependent on the chosen metric. This is not overly surprising. And the uncertainty challenge used actually a scaled flavor of the pinball loss function. We'll be getting back to this error metric in a minute. And overall, the M5 uncertainty challenge demonstrate that we don't have the means to eliminate uncertainty with the forecasting method that we have, not even close. And thus, it is not at all a surprising result, considering that if we are looking at the sales data from a retail store, sales tend to be erratic and intermittent. However, it really, I would say, emphasize the importance of embracing uncertainty instead of just dismissing the case entirely. However, it is remarkable to note that that basically supply chain software vendors were basically all absent from the top 50 ranks also of this forecasting competition, which is all the more intriguing considering that those vendors are all boasting some kind of supposedly superior state-of-the-art forecasting technology of their own. Now, this lecture is a part of a series of supply chain lectures. This present lecture is the first lecture of what will be my 5th chapter in this series. And it will be dedicated, this 5th chapter will be dedicated to predictive modeling. Indeed, gathering quantitative insights is necessary to optimize a supply chain. Whenever a supply chain decision is made, and it can be deciding to buy materials, to produce a certain product, to actually move stock from one place to another, to increase the price or decrease the price of something that you sell, then this decision comes with a certain anticipation of the future demand that is going to be fulfilled through this decision. More generally, every single decision, supply chain decision, comes with a built-in expectation about the future. This expectation can be implicit and hidden. However, if we want to improve the quality of our expectation about the future, then we need to reify this expectation, which is typically done through a forecast, although I would like to specify that this forecast doesn't necessarily have to be a time series forecast. The 5th and present chapter is named predictive modeling rather than forecasting. There are 2 reasons for this choice of naming. The first one is that forecasting is almost invariably associated with time series forecasting. However, as we will see in this chapter, there are many supply chain situations that don't really lend themselves to time series forecast and to the time series forecasting perspective. Thus, in this regard, predictive modeling is a more neutral term. The second is that it's modeling that holds the true insight, not the models. And we are looking for modeling techniques, and it's through modeling techniques that we can expect to be able to cope with the sheer diversity of situations as they are encountered in real-world supply chains. Thus, the present lecture is used as a prologue for our predictive modeling chapter to establish that predictive modeling isn't some kind of wishful thinking about forecasting, but that it qualifies as a state-of-the-art forecasting technique, and that comes on top of all the other benefits that will gradually come clear as I progress through this chapter. The rest of this lecture will be organized in 3 parts. First, we will review a series of mathematical ingredients which are essentially the building blocks of the REMT model. Second, we will actually assemble those ingredients in order to construct the REMT model and just the way it was during the M5 competition. And third, we will discuss what can be done to improve upon the REMT model, and also to see what could be done to improve upon the forecasting challenge itself, the forecasting challenge as it was presented in the M5 competition. The uncertainty challenge of the M5 seeks to compute quantile estimate of future sales. A quantile is a point in a one-dimensional distribution, and by definition, a 90% quantile is the point where there is 90% chance to be below this quantile value and 10% chance to be above this quantile value. The median is, by definition, the 50% quantile. The pinball loss function is a function that comes with a deep affinity for quantiles. Essentially, for any given tau, a value between 0 and 1, and tau essentially can be interpreted from our supply chain perspective as a service level target. So for any tau value, the quantile associated to tau happens to be the value within the probability distribution that minimize the cutoff, that minimize the pinball loss function. And on the screen, we see a straightforward implementation of the pinball loss function. You can see that it's basically just a declaration of the function and one line for the logic. And this logic, by the way, is written in Envision, the domain-specific programming language of Lokad, dedicated to supply chain optimization purposes, although the syntax is fairly, I would say, Python-like and should be relatively transparent to the audience. And so if we try to unpack this little bit of code, we have y, which is the real value. We have y hat, which is our estimate. And we have tau, which is our quantile target. Again, the quantile target is fundamentally the service level target in supply chain terms. And we see that the under forecast comes with a weight equal to tau, while the over forecast comes with a weight that is equal to 1 minus tau. The pinball loss function is a generalization of the absolute error. And indeed, if you go back to this tau equals 0.5, if we go back to the quantile at 50%, which is to say the median, we can see that the pinball loss function is just the absolute error. And indeed, if we have an estimate that minimizes the absolute error, what we get is an estimation of the median. Now, in red, what you can see on the screen is basically a plot of the pinball loss function. And as you can see, this loss function is asymmetric. And this is the whole point, is that we are, through an asymmetric loss function, we can get not the average or median forecast, but we can have a forecast with a control bias, which is exactly what we see. We want to have a quantile estimate. And the beauty of the pinball loss function is that its simplicity. If you have an estimate that minimizes the pinball loss function, then you have a quantile forecast by construction. And thus, if you have a model that happens to have parameters, and you just steer the optimization of the parameters of those models through the lenses of the pinball loss function, what you will get out of your model is essentially a quantile forecasting model. The M5 uncertainty challenge presented a series of 4 quantile targets at 50%, 67%, 95%, and 99%. I typically refer to such a series of quantile targets as a quantile grid. quantile grid forecasts are not quite probabilistic forecasts. It's close, but not there yet. With a quantile grid, we are still cherry picking our targets. And for example, if we say that we want to produce a quantile forecast for the 95%, then the question becomes why 95, why not 94 or 96? So that's a question that is left essentially unanswered. We will have a closer look at that later on in this chapter, but not in this lecture. Let's suffice to say that essentially the main gain that we have with probabilistic forecasts is to eliminate entirely this cherry-picking aspect of I would say, the quantile grids. Most of the audience is probably familiar with the normal distribution, the Gaussian, a bell-shaped curve that occurs very frequently in natural phenomena. A count distribution is a distribution of probabilities over every integers. And they are, I would say, unlike continuous real distribution, like the normal distribution, that gives you a probability for every single real integers, count distributions only cares about essentially non-negative integers. There are many classes of count distributions. However, today our interests lie in the negative binomial distribution, which happen to be used by the REMT model. The negative binomial distribution comes with two parameters, just like the normal distribution, which also control effectively the mean and the variance of the distribution, again, just like the normal distribution. If we basically choose for a negative binomial distribution the mean and the variance so that the bulk of the mass of the probability distribution is far from zero, we have essentially a behavior for the negative binomial distribution that asymptotically converge to a normal distribution behavior. If we were to collapse all the probability values toward the nearest integers. However, if we basically look at distributions where the means is small, especially compared to the variance, we will see that the negative binomial distributions start to very significantly diverge in terms of behavior compared to a normal distribution. In particular, if we look at small mean negative binomial, we'll see that those distribution becomes highly asymmetric, which is very unlike the normal distribution, which remains completely symmetric no matter which mean and variance you pick. On the screen, a negative binomial distribution plotted through Envision. The line of code that was used to produce this plot is on display below. And the function takes two arguments, which is expected as this distribution has two parameters. And the result is just a random variable that gets displayed as an histogram. I am not going to delve into the fine print of the negative binomial distribution here in this lecture. This is straightforward probability theory. We have, in the literature, we have explicit closed form analytical formulas for pretty much everything, for the mode, for the median, for the cumulative distribution function, the kurtosis, etc., etc., etc. So the Wikipedia page gives you a pretty decent summary of all those formulas, so I invite the audience to have a look if they want to know more about this specific kind of count distribution. Let's move to the innovation space state model, or ISSM. The innovation space state model is a long and impressive sounding name to do something that is quite simple, in fact. The ISSM is a model that transforms a time series into a random walk. With ISSM, you can turn just a plain vanilla times average time series forecast. And when I say average, I mean, again, a forecast where for each period you will have one value set at the average. into a probabilistic forecast, and not just a quantile forecast, but directly a probabilistic forecast. And on the screen, what you can see is a complete ISSM implementation written once again in Envision. So we can see that it's only a dozen or so of lines of code, and actually even most of those lines of code are not even doing much. So ISSM is literally very straightforward, and it would be very straightforward to re-implement this piece of code into any other language, Python, for example. So let's have a closer look at the fine print of those lines of code. In the line 1, I am actually specifying the range of the periods where the random walk will happen. So here we are, from the perspective of the M5, we want a random walk for a period of 28 days. So we have 28 points, 1 point per day. At line 3, 4, and 5, we introduce a series of parameters that will control the random walk itself. The first parameter is the dispersion. The dispersion will be used as an argument to control the shape of the negative binomials that occur inside the ISSM process. Then we will have alpha, which is essentially the factor that controls the exponential spoofing process that also happens inside the ISSM. And then we have at line 5 the level, which is just the initial state of the random walk. And finally, at line 6, we have a series of factors which are typically intended to capture all the calendar patterns that we want to embed in our forecasting model. Now, the values from line 3 to 6 just comes with mock initialization for the sake of concision. I will get to how those values are actually optimized in a minute, but here all the initialization that you see are just mock values. I'm just even drawing random values for the baseline. We will get how, in the reality, if you want to use this model, you will need to properly initialize those values, which we will do just later in this lecture. Now, let's have a look at the core of the ISSM process. So the core starts at line 8, and it starts with a loop of 1,000 iterations. So I just said that the ISSM process is a process to generate random walks. So here what we are doing is that we are doing 1,000 iterations. So we are going to do 1,000 random walks. We could have more, we could have less. It is a straightforward Monte Carlo process. Then at line 9, we are doing a second loop. This is the loop that iterates 1 day at a time for across the period of interest. So we have the outer loop, which is essentially give us 1 iteration per random walk. And then we have the inner loop, which is 1 iteration is just 1 day ahead, moving from 1 day to the next within the random walk itself. Now, we have at line 10, we have a keep level. So keep level just say that these parameters is going to be mutated within the inner loop, not within the outer loop. So that means that level is something that varies when we go from 1 day to the next, but when we go from one random walk to the next through the Monte Carlo loop, this level is going to be reset to its initial value that is just declared above. Now, line 11, we compute the mean. So the mean is the second parameter that we use to control the negative binomial distribution. So we have the mean, we have the dispersion, we have a negative binomial distribution. And at line 12, we draw a deviate according to the normal binomial distribution. Drawing a deviate just means we take a random sample extracted from this count distribution. And then at line 13, we update this level based on the deviate that we have just seen. And the update process is just a very simple exponential spoofing process. And it's guided by this alpha parameter. If we take alpha very large, equal to 1, that means that we put all the weight to the last observation, On the contrary, if we were to put alpha equals 0, it would mean that we would basically have zero drift. We would stay true to the original time series as defined in the baseline vector. By the way, in Envision, when it's written day.baseline, what we see here is that day is a table. So it's a table that has, that's in DMFI that would have 28 values. And baseline is just a vector that belongs to this table. Then line 15, we collect all the deviates and we sum them through sumday.q. We sum them into one variable named total. So we have essentially within one random walk, we have summed all the deviates that were collected for every single day. So we have the total of the sales over 28 days. And then finally, at line 16, we are essentially gathering, collecting those samples into a REMT. A REMT is a specific object in Envision, which is essentially a probability distribution over Z relative integers, positive and negative. And so in summary, what we have is the ISSM is a random generator of one-dimensional random walk. And in the context of sales forecasting, you can think of those random walks as possible future observations for the sales themselves. You see, that's where it's interesting, is that we don't think the forecast as the average or the median. We literally think our forecast as one possible instance of one future. And at this point, we have gathered everything that we need to start assemble the REMT model, which we are going to do right now. The REMT model adopts a multiplicative structure which is reminiscent of the Alt-Winters forecasting model. Every day gets a baseline, and which is a single value that happens to be the product of 5 calendar effects. And we have namely the month of the year, the day of the week, the day of the month, Christmas, and Halloween effects. And again, this logic is implemented as a very concise Envision script. And here, Envision, we see why Envision is kind of interest. Envision has at its core a relational algebra. And this offers broadcast relationship between the table, which are very practical for this very situation. The 5 tables that we have constructed, one table per calendar pattern, are constructed as grouping table. So what we have is that we have the day table, and the day table has a primary key called date. So date is the primary key table of the day table, and thus when we write that we declare a new table with a by aggregation and then we have the date, what we are building is a table that have directly a broadcast relationship with the day table. Indeed, if we have, let's say, a specific look at the day of week, for example, table, line 4, what we are building is that we are building a table that will have day of week that will have exactly 7 lines. And every single line of the table day will be associated to one and only one line of day of week. And thus, if we put values in this day of week table, then we can broadcast those values quite naturally, because on the recipient side, on the day side, for every single line will have one line to match in this day of week table. Now, that is exactly what is happening at line 9 with the vector day.baseline, which is computed as the plain multiplication of the 5 factors on the right and on the right side of the assignment. And all those factors are essentially first broadcast to the day table, and then we proceed with a simple line-wise multiplication for every single line in the day table. And again, this is just a a fancy array programming feature of Envision. Now, what we have is we have now a model that have a few dozens of parameters. We can even count those parameters. We have essentially 12 parameters for month of year, from 1 to 12. We have 7 parameters for day, parameter values for day of week. We have 31 parameters for day of month. However, we are not going to learn, in the case of the M5, we are not going to learn one parameter value for all those values for every single SKU. We would end up with a massively large number of parameters that would most likely vastly overfit the Walmart dataset. So instead, at the M5, what was done was to leverage a trick that is known as parameter sharing. This is parameter sharing means that instead of learning distinct parameters for every single SKU, we are going to establish subgroups and then learn those parameters at the subgroup level and then use the same values within those groups for those parameters. Parameter sharing is a very, very classic technique that is extensively used in deep learning, although it was predating quite extensively deep learning itself. Now, during the M5, the month of year and day of week were learned at the store department aggregation level. I will get back in a second to the various aggregation levels of the M5. And the day of month value was actually hard-coded factors that were set at the state level. And when I say the state, I'm meaning the state as in the United States, so California, Texas, etc. And during the M5, all those calendar parameters were simply learned as direct averages over their related scope. So it's a very, very direct way to actually set those parameters, is that you just take all the SKUs that belong to the same scope, you average everything, you normalize, and here you are, you have your parameter. And now, at this point, we have gathered literally everything to assemble the REMT model. And we have seen how to build the daily baseline, which embeds all the calendar patterns. The calendar patterns have been learned through direct averages over a certain scope, which is a crude but effective learning mechanism. And we have seen that the ISSM transforms a time series into a random walk. So now we are only left with establishing the proper values for the ISSM parameters, namely alpha, the parameters that was used for the exponential smoothing process that happened inside the ISSM. We had the dispersion, which is a parameter that is used to control the negative binomial distribution. And we have the initial value for the level that is used to initialize our random walk. During the M5 competition, the team from Lokad leveraged a simple grid search optimization to learn those remaining 3 parameters. Grid search essentially means that you iterate over all the possible combinations of those values going through small increments at a time. Grid search was directed using the pinball loss function that I've just described previously to steer the optimization of those 3 parameters that remains for every single SKU. Grid search is probably one of the most inefficient form of mathematical optimization. However, considering that we have only 3 parameters and that we only need to perform 1 optimization per time series, and that the M5 dataset itself is fairly small, it was kind of okay for the M5 competition. So far, we have presented how the REMT model operates at the SKU level. However, in the M5, there were 12 distinct aggregation levels. The SKU level, being the most disaggregated level, was the most disaggregated level. So the SKUs is storage keeping unit. The SKU level is literally one product in one location. That's a SKU. If you have the same product in 10 locations, then you have 10 SKUs. although the SKU is arguably the most relevant aggregation level for supply chain, indeed, nearly all inventory-related decisions, replenishment, assortment, etc., happens at the SKU level. Although this is why we focus so much. But again, the M5 was first and foremost not a supply chain competition, but a forecasting competition, and thus there were a lot of emphasis on the other aggregation level. And so on the screen, these three summarize the aggregation level that were present in the M5 dataset. You can see that we have the states, the 3 states, California, Texas, Wisconsin at the top. And in order to deal with the higher aggregation levels, 2 techniques were used by this team from Lokad. Essentially, either to sum the random walks, so you do the random walks at a lower aggregation level, you sum them, and then that gives you random walks at a higher aggregation level, or to restart the learning process entirely, directly jumping to the higher aggregation level. In the M5 uncertainty challenge, the REMT model was the best at the SKU level, but it wasn't the best at the other aggregation level, although it did very good overall across the board. My own working hypothesis on why was not, the REMT model the best at all levels is as follows. This is an hypothesis. We didn't actually test that. My own working hypothesis is just that the negative binomial distribution offers 2 degrees of freedom, through the 2 parameters. Thus, when we are looking at fairly sparse data, as it is found at the SKU level, those 2 degrees of freedom happens to be the right balance between underfitting and overfitting. And again, this balance is we have only 2 parameters because the data is fairly sparse. However, as we move toward higher aggregation level, the data becomes a lot more dense, a lot more rich in term, and thus the trade-off is probably shifting toward something that would be better suited to capture more precisely the shape of the distribution. We would need a few extra degrees of freedom. Nothing fancy, probably just 1 extra parameters or 2 extra parameters would be enough. And so I suspect that just I would say increasing the degree of parametrization of the count distribution that is used at the core of the REMT model would have gone a long way to basically achieve something very, very close, if not, being directly state-of-the-art for the higher aggregation levels. Nevertheless, we didn't have time to do that yet, so we maybe revisit the case at some point in the future. And this concludes essentially what was done by this team at Lokad during the M5 competition. Let's discuss what could have been done different or better even. The REMT model is a low-dimensional parametric model with a simple multiplicative structure. However, the process that was used to obtain the values of the parameters during the M5 is something that is somewhat accidentally complicated. It was, during the M5, a many-stage process where each calendar pattern having its own ad hoc-ish special treatment. And the whole thing was ending up with a bespoke grid search that was in order to basically complete the REMT model. The whole process was quite time-consuming for data scientists, and I suspect in production settings it would be quite unreliable due to the sheer amount of ad hoc code that is involved. I mean, nothing that can't be fixed, but still it really deserves to think a little bit about what can be done better. In particular, my take is that we can and should unify the learning process of all the parameters as a single stage process, and or at the very least unify the learning process so that it's the same method used repeatedly. Nowadays, Lokad is using differentiable programming to do exactly that. Differentiable programming removes the needs for those ad hoc aggregation as far as the calendars patterns are concerned. Differentiable programming also removes the needs for remove the tedious problem of precisely ordering the extraction of the calendar patterns by extracting all the calendar patterns in one go. And finally, as differentiable programming is an optimization process of its own, it basically replaces the grid search with a much more efficient optimization piece of optimization logic. We will be reviewing how differentiable programming can be used for predictive modeling in the context of supply chain purposes in greater details in later lectures in this chapter. Now, one of the most surprising results of the M5 was that no statistical pattern remained unnamed. We had literally cyclicities, state, spread, and drift. Those 4 patterns were all it took to achieve state-of-the-art forecasting accuracy at the M5. Cyclicities are all calendar-based, and none of them is even remotely surprising. The state can be represented as a single number that represents the level achieved by the SKU at this point of time. The spread can be represented with a single number that is the dispersion used to parameterize the negative binomial, and the drift can be represented with a single number associated with the exponential smoothing process that happened within the ISSM. So we didn't even have to include the trend, which was too weak for a 28-day horizon. While when we look at the total 5 years aggregated sales for the M5, as it is displayed on the screen, so that's essentially the total aggregation of all the sales for the entire duration of the data set. This aggregation clearly shows a modest upward trend, but nevertheless, the REMT model operates without, and it had basically 0 consequence in terms of accuracy. And while the absence of evidence should not be confused with the evidence of absence, the REMT model achieving number 1 at the SKU level really begs the question, is there any other pattern to capture? And any pattern that we have missed? At the very least, the performance of the REMT model shows that none of the more sophisticated models that were involved in this competition, say gradient boosted trees or deep learning methods, did capture anything beyond those 4 patterns. Indeed, if any of those models had managed to substantially capture anything, this model would have vastly overperformed the REMT model at the SKU level, which they did not. And the same can be said about all the more fancy, I would say, statistical methods like ARIMA. Those models have also failed to capture anything beyond what this very simple multiplicative parametric model has captured when we look to the model, I would say, through the lens of the accuracy. And so the Occam result tells us that unless we can find some very good reason to think that a pattern eludes us, or to think a very good reason for some very interesting property that would trump, the simplicity of this model, I mean, we don't have any reason to use anything but a model that is at least as simple as the REMT model. However, a series of patterns were absent from the M5 competition due to the very design of the M5 dataset. Those patterns are important, and in practice, any model that ignores them is going to work badly in a real retail environment. I'm basing this statement on my own experience. So first, we have the product launches. Indeed, the M5 only included products that had at least 5 years' worth of sales history. This is a widely unreasonable assumption as far as supply chain is concerned. Indeed, FMCG products only live a couple of years, and thus in an actual store, there is always a significant portion of the assortment that has less than 1 year worth of sales history. Furthermore, when we are looking at products that have long lead times, there are numerous supply chain decisions that have to be taken even before the product has a chance to be even sold even once in any store. Thus, we need to have forecasting model that can even operate with 0 sales history for this given product. The second pattern that was of critical importance is stockouts. There are stockouts in retail, and the M5 dataset ignored entirely stockouts. However, stockouts are capping the sales. If a product is out of stock in the store, obviously this product is not going to be sold this day in the store. And thus, stockouts introduce a very important bias in the sales that we observe. And the problem in the case of Walmart and general merchandise store is even more important than it seems, is even more, I would say, complicated, sorry, than it seems, because the electronic records that capture the stock on hand values cannot be fully trusted. Indeed, there are numerous inventory inaccuracies, and this needs to be taken into account as well. Third, we have promotions. The M5 did include historical pricing data for however, the price data was not provided for the period to be forecast. And as a result, it appears that no contender in this competition, no top-ranked contender, managed to leverage the price information to truly improve the forecasting accuracy. The REMT model does not use the pricing information at all. And more generally, I would say, beyond the fact that we were missing the price information for the period of the forecast, promotions are not just pricing. A product can be promoted by just being put forward in a store. If you decide to have a product that is moved to a retail gondola, it's going to be significantly boosting the demand, independently on whether you have lowered the price of the product or not. Thus, and also with promotion, we need to start to think in terms of cannibalization and substitution. And so I would say, overall, I would say maybe while my judgment might be a tiny bit severe, from a supply chain perspective, the M5 dataset is a bit of a toy dataset. The M5 public dataset remains probably the best public dataset in existence to carry a supply chain benchmark, but yet it's still nowhere near something that would be truly equivalent to an actual production setup in even a modestly sized retail chain. However, the limits of the M5 aren't just missing data from the M5 dataset. Supply chain-wise, there are fundamental problems with the rules that were used to conduct the M5 competition. Again, I'm saying that from a supply chain perspective, not from a forecasting perspective. The first fundamental problem is to not confuse sales with demand. We have already touched this problem with the stockout. What is truly of interest from a supply chain perspective is to anticipate the demand, not the sales. However, the problem goes deeper than it seems. Indeed, the proper estimation, quantified estimation of the demand is fundamentally something that is an unsupervised learning problem. Indeed, it is not because arbitrary choices have been made about what is the applicable assortment in a store. And so it's not because you decide that a product should not be in one store that the demand for this product should not be estimated nonetheless. Again, we have to estimate the demand of products irrespectively of whether they are, effectively part of the assortment in any given store. Also, the second aspect is that quantile forecasts are less than probabilistic forecasts. Cherry-picking service level leaves gaps in the picture, and it's essentially quantile grids are fairly weak in terms of supply chain usage. A probabilistic forecast delivers a much more complete vision because we have the complete probability distribution, and it eliminates this class of problem. The only key downside of probabilistic forecasts is that they require more tooling, especially when it comes to actually do anything with the probabilistic forecast downstream after the forecast has been produced. By the way, the REMT model actually delivers something that qualifies as a probabilistic forecast because through the Monte Carlo process, you can generate an entire probability distribution. You just have to tune the amount of Monte Carlo iterations. Third, retail customers don't really care in retail about the SKU perspective. They don't care about the service level that you can achieve on any given SKU. The perception of customers in a general merchandise store like Walmart is driven by the basket. Indeed, customers walk into a Walmart store not with one product in mind. Typically, they have a whole shopping list in mind. And thus, they are, and from that part, there is not only they have a whole list, but fortunately, there is also tons of substitutes in the store. And thus, the problem of using a single SKU metric to assess the quality of service is that it completely misses to assess what customers effectively perceive as the quality of service in the store. In conclusion, as a time series forecasting benchmark, the M5 is solid both in terms of data sets and in terms of methodology. However, the time series perspective itself is pretty lacking as far as supply chain is concerned. Time series do not reflect data as they are found in supply chains. Time series do not reflect problems as they present themselves in supply chains. And during the M5 competition, there were plenty of vastly more sophisticated methods among the top ranks. However, in my view, those models are effectively dead ends. They are already too complicated for a production usage, and yet they already embrace a time series perspective so much that they don't have any operational room to grow into the sort of fresh perspective that we need to adjust those models to our own supply chain needs. On the contrary, a very simple, as a starting point, the REMT model is as good as it gets. This is a very simple combination of ingredients that themselves are very simple on their own. And furthermore, it doesn't take that much imagination to see that there are plenty of ways to use and combine those elements way beyond the sort of specific combination that we have put together for the M5. Thus, the rank achieved by the REMT model at the M5 demonstrates that essentially, until proven otherwise, we should essentially stick to very simple model as we don't have any compelling reason to go for very complicated models that are almost guaranteed to be harder to debug, harder to operate in production, and will consume vastly more computing resources. In the lectures to come in this 5th chapter, we will see how we can use those ingredients that were part of the REMT model, but also quite a few other ingredients in order to address the extensive variety of predictive challenges as they are found in supply chain. And the key thing to remember is that the model is unimportant. It's the modeling that matters. Excellent. Questions? So let's have a look. Okay, the first question is Sharam Dabdervari. I'm very sorry for butchering the names, please. I deeply apologize. Why negative binomials? What was the reasoning when you selected that? That's a very good question. Well, it turned out that if there is a world bestiary of count distributions, and there is probably 20-something very widely known count distributions. At Lokad, we did test a dozen for our own internal needs. It turned out that Poisson itself, which is a very, very simplistic count distribution with just one parameter, works fairly well when the data is very, very sparse. So Poisson is quite good, but actually the M5 dataset was a bit richer. So there is, in the case of the Walmart dataset, we tried basically count distribution that were having a few more parameters. And then it seems to work. I guess we don't have the proof that it's actually the best one that there is. There is probably better. The negative binomial has a few key advantages. The implementation is very straightforward. It is also an extensively studied count distribution. So again, it's not you have like very widely known algorithm, not just to actually compute the probabilities, but also to sample or deviate to obtain the mean or the cumulative distribution. So all the tooling that you can expect in terms of count distribution is there. This is not necessarily the case for all the count distributions. So I would say there is a third degree of pragmatism that went into this choice, but also a bit of logic. As I was saying, there is the number of degrees of freedom. With Poisson, you have 1 degree of freedom. You could use negative binomial has 2. Then you can use tricks like zero inflated negative binomial, which gives you kind of 2.5 degree of freedoms, etc., etc. So I would not, I think it's a valuable ingredient. It's something that is nice to have under your belt. But I would say there is no specific definitive values to this count distribution. A question from Alexei Tikhonov. There were other supply chain optimization software vendors in the M5, but nobody used light models that scale well in production. What does majority use heavy machine learning models? So first, I would say we have to distinguish, to clarify. The M5 was done on Kaggle, a platform for data science. In Kaggle, you have a massive incentive to use the most complicated machinery possible. The data set is small. You have a lot of time. You have months. And so essentially, and the idea is that to be the top rank, you just have to be 0.1% more accurate than the other guy. This is all that matters. Thus, in virtually every single Kaggle competition, you would see that the top ranks are filled with people that did pretty much insane thing in terms of engineering, which are very, very complicated, just to kind of get a 0.1% extra accuracy. So basically, the very nature of being a forecasting competition gives you, I would say, a strong incentive to try everything, including the most insane heavyweight model that you can find. So that I would say that explains why most of the contenders are doing that. Then, if we say, are people actually using this model, those I would say heavyweight machine learning models in production? My own casual observation is absolutely no. It's actually exceedingly rare. Literally, I've talked, but here that's the casket of the CEO of Lokad, a supply chain software vendor. I've talked to hundreds of supply chain directors. Literally 90% plus of the large supply chains are operated through Excel. So, but again, I've never seen any large-scale supply chain operated with gradient boosted trees or deep learning networks. If we put aside Amazon, Amazon is probably one of a kind. There is maybe half a dozen companies. Amazon, Alibaba, and GD.com and a few others, you know, the very, very big e-commerce, super giant e-commerce that are actually using this sort of tech, but they are very, I would say, exceptional in this regard. They are absolutely your mainstream, you know, large FMCG company or large retail brick and mortar retail company is not using these sort of things in production. A question from Alexei Ivasyuk. It's strange that you mention a lot of mathematical and statistical terms, but you ignore the nature of retail sales and the main influence factors. I would say yes. I mean, this is. I'm not sure that it's actually a question. This is more like a comment. But my question to you is what do you bring to the table? Because you see, that's what I was saying when supply chain vendors who are boasting superior forecasting technology, they were all absent. You see, that's something that is very, very interesting to me, is that why is it that if you have an absolutely superior forecasting technology, that you happen to be absent whenever there is something like a public benchmark? Strange. Or the other Occam razor, the other explanation, where it's just that people are bluffing, you know. And again, it doesn't take long to kind of, you know, suspect that a large vendor might be tempted to push a little bit the quality of their product, you know, to push the claim a little beyond what it actually is. I don't think that it requires, you know, so much imagination. So that would be, you know, my perspective. Then concerning the sort of nature of retail sales and main influence factors, I'm not sure what you were referring to. I listed the patterns that were used, and by using those literally 4 patterns, it was in terms of accuracy, the REMT model did end up #1 at the SKU level. So I would say if you take the proposition that there are vastly more important patterns out there that are actually much more important than those ones, I would say, yes, why not? Absolutely. But the burden of proof is on you, because obviously, you know, where were you when this competition took place? Because you see, again, my own suspicion is that Occam razor is that if among 900 plus teams those patterns were not observed, well, they were probably not there. Or capturing these patterns is so outside the realm of what we can do with the sort of technology that we have, that it's, for now, it's as if, from a practical perspective, as if those patterns do not exist. Maybe they are, but if they are widely outside our capacity to capture them, it doesn't really benefit to us from a practical, grounded supply chain perspective. A question from Jess Bankston. Did any competitors in M5 apply idea which, while not beating Lokad, would be valuable to incorporate, especially for generic application? Honorable mention. Again, I am not sure. I am paying a lot of attention to my competitors. I'm pretty sure that my competitors are paying some attention to Lokad. I did not see that. So again, I believe that, you see, the REMT model was really one of a kind. It's completely unlike what was done by essentially almost all the other top 50 contenders for either task. The other participants were using things that were much, much more classical, I would say, in machine learning circles. I'm not saying they were very, very nice ideas. For example, some people did actually use very smart, fancy tricks to do data inflation on the Walmart dataset to kind of make it much bigger than it was to gain some extra % of accuracy. This is what was done, by the way, by the contender that ranked #1 in the uncertainty challenge. This was a very nifty trick, especially data augmentation, sorry, not data inflation, data augmentation, that's the proper term. Data augmentation is commonly used in, I would say, for deep learning techniques, but here it was used with gradient boosted trees in ways that are, I would say, it was maybe not the first time, but it was, I would say, fairly unusual. So that they were, I would say, fancy, very smart data science tricks that were demonstrated during this competition. I am not too sure about whether those tricks generalize well to supply chain, but I would say yes. I will probably mention a couple of them during the rest of this chapter if the occasion occur, the opportunity occur. Another question from Jess Bankston. Did you estimate higher levels by aggregation, by aggregating your SKU levels, or by freshly calculated middle out for higher level? If both, how did they compare? So essentially, the optimization, that's the problem that you have with quantile grids more generally, is that you tend to optimize models separately for each target level. And so what can happen with quantile grids is that you can get quantile crossing. So that means that just by a flock of numerical instabilities, you end up with your 99% quantile that end up lower than your 97 quantile. This is inconsequential. Typically, what you do is that you just reorder the values, but fundamentally, that's the sort of problem that I was referring to in terms of quantile grids being, I would say, not quite probabilistic forecast, is that you have tons of nitty-gritty details to solve, but the reality is that you need to solve them, but they are kind of inconsequential in the grand scheme of things. And so when you transition toward probabilistic forecast, those problems do not even exist anymore. So that would probably be, the answer to this question. Another question from Alexei Tikhonov. If you were designing another competition for software vendors, what would it look like? Frankly, I don't know. And this is a very, very difficult question. I believe that, despite all my heavy criticism, as far forecasting benchmark goes, the M5 is the best that we have. Now, in terms of supply chain benchmark, the problem is that I'm not even completely convinced that it's even possible. You see, when I hinted that some of the problems are actually of the type of that require unsupervised learning, this is tricky. When you enter the realm of unsupervised learning, suddenly, you have to give up on having metrics. And by the way, this is not just me. It's the entire realm of I would say, advanced machine learning is still struggling as a community to come to terms with what does it even mean to operate superior, learning tools, automated learning tools in a realm where you are unsupervised. Suddenly, how do you even benchmark those sort of things? Again, for the audience that wasn't there for my lecture about machine learning, in supervised setting, you are essentially trying to accomplish a task where you have input, output, and then you have a metric to assess the quality of your outputs. When you are unsupervised, it means that you don't have labels. You don't have, you're only trying to predict, but you don't have anything to compare to. And so things becomes much more difficult. And also, I would point out that in supply chain, there are many things where you can't even backtest your, beyond, I would say, the unsupervised expect, there is even the backtesting perspective that is not completely satisfying. For example, the forecasting the demand is going to generate certain type of decisions, such as pricing decision. If you decide to adjust the price up or down, that's a decision that you made, and it will forever influence the future. So you can't go back in time to say, okay, I'm going to make a different demand forecast and then take a different pricing decision and then let the history repeat itself, except that this time I have a different price. So there are plenty of aspects where even just the backtesting idea don't even work. So that's why I believe that a competition is something that is very interesting from a forecasting perspective. it is useful as a starting point for supply chain purposes, but then we need basically to do better for and different if we want to end up with something that is truly satisfying for supply chain purposes. And that's what I am going to do in this chapter about predictive modeling. I'm going to show that why is modeling such worthy of such, I would say, focus. At least that's the proposition that I have for you. A question from Alexandro Beretta. Can this methodology, I suspect that you're referring to, be used in situations where you have few data points? I would say absolutely, absolutely. This sort of structured modeling that has been demonstrated here with the REMT model shines brightly in situations where you have very, very sparse data. And the reason is very simple. You can embed a lot of knowledge, human knowledge, in the very structure of the model. So you see, the structure of the model is not something that was, pulled out of thin air. It is literally the consequence of the Lokad team understanding the problem. You see, for example, when I say I look at the calendar patterns, when we look at the calendar patterns such as day of week, month of year, etc., we didn't try to kind of discover those patterns. The Lokad team knew from the start that those patterns were already there. The only, I would say, uncertainty in this regards was the sort of respective prevalence of the day of the month pattern, which tend to be weak in many situations. It's in the case of the Walmart setup, it was just due to the fact that there is this stamp program in the US that this day of the month pattern is as strong as it is, and the existence or not of the trend. You see, so essentially all the patterns were already known and identified right from the start. And so it was just a matter of choice of including the pattern or leaving it out. And if you have little data, this sort of approach works exceedingly well, because whatever learning mechanism you're trying to use, this mechanism is not trying to, grind at random structure out of the little data point that you use. On the contrary, it's going to extensively leverage the structure that you have imposed. So yes, it begs the question, what if the structure is wrong? But that's why supply chain thinking and supply chain understanding is really important, so that you can make the right decision. Then in the end, you have ways to assess whether your calls, your arbitrary decisions in this regards were good or bad. But fundamentally, this is something that happens very, very late in the process. And so we will be illustrating later in this very chapter about predictive modeling, how structured modeling can be used effectively on datasets that are incredibly sparse, as the one that I would say top of my head happens in aviation, hard luxury, MROs of all kind. Those are the situations where you have like exceedingly sparse data and you still need to operate. And that's why and for those situations, those structured models really shine. Excellent. So the next lecture will happen February 2nd. That will be Wednesday, same time of the day, 3 p.m. time of Paris. See you then.